Welcome back, Regents physics students. This is the 5th lesson in our waves topic. Today's lesson is about something called wave interference. The first thing we're going to learn is something called the principle of superposition. It tells us what happens when two waves travel toward each other, approach and meet and overlap. The net y displacement is just the sum of the two individual displacements. In other words, if this were a wave on a spring 2 meters tall and this one was 1 meter tall, the spring, when the waves met each other, would rise 2 plus 1 or 3 meters. The heights of the waves add, but the widths do not. Okay, so only the heights add. Okay, so what I'm going to do is go through some examples to show you this effect at work. So this is the first example. It is two square waves. Now on a spring you would not be able to really create a spring like this, like rising your hand up instantaneously, letting that travel through and then pulling straight back down. But you could do this kind of wave in electrical wires with voltages and electric fields passing through the wires. You can have, the signal rise up almost instantaneously, stay up as that signal's traveling through the wire, and then drop back down pretty much instantaneously. Create a square wave on one side of the wire and then a square wave on the other side of the wire. So we're just going to use meters, pretending that we can do this on a spring. So let's suppose we make a spring wave here 3 meters tall and 3 meters wide. It's basically a square. And on this end we send a wave that's 1 meter tall and 1 meter wide. So these waves come toward each other. When they meet, they do not bounce off each other. They don't crash and stop. What happens is they meet and then they stack right on top of each other. We use, again, the principle of superposition, that the net y displacement is the sum of the y displacements at all points on the waves. So then it would look like this, with the total height being 4 meters. But notice the two widths of the two original waves did not increase or decrease. And then after, this is a very important point about waves, the waves don't bounce off each other, they pass through each other. So you see this original wave on the right emerges on the left, the same exact wave. And the wave that was on the left emerges on the right. They pass through each other. And you know this from everyday experience. Let's suppose you've got two people, one right here and one right here, okay? And they're talking simultaneously. And what happens is, in the middle, someone sitting hears both of their voices sort of jumbled together. But this person, represented by the green pencil, can hear this person. The waves meet in the middle and pass through. So this person over here, maybe this is me, this is you, my sound waves would pass through your sound waves and get to your ear. You'd hear what I was saying. And same with me. I would hear what you were saying. The waves pass through. Okay, so waves pass through. They don't bounce off or stop each other. Okay. Another example is right here. We have a wave like the original 3 meters tall, 3 meters wide, and this time this 1 meter wide wave is with a negative y displacement of 1 meter. You see that when the two waves meet, in the middle we have 3 meters plus negative 1 meter, which gives us just 2 meters of displacement. And again, the widths remain unchanged. And then after, the waves pass through each other. So on the homework, you're going to see many different shapes, and you're going to just try and add them the best that you can with the principle of superposition. A couple other things that about interference and the principle of superposition that I want to mention: something called constructive interference and destructive interference. Constructive interference is when two waves that are of the same direction displacement meet. Then what happens, like here, this wave A has maybe a positive 1 meter displacement and B also a positive 1 meter displacement. Both waves, I try to draw them the same size. They're both 1 meter wide, so that's the intention, even though they didn't quite come out the same. When the waves meet and overlap in the middle, The net displacement is 1 plus 1, principal superposition, or 2 meters. And the width is still 1. It doesn't, that just one wave stacks on top of the other. So the widths don't add, okay? And then after, again, B ends up passing through, A passed through also. So that was constructive. In the beginning, in the middle, they added up and created a larger wave. Okay, so that's constructive. You could also have two troughs coming instead of two crests and make a big down trough, and that's also considered constructive interference. The other kind of interference is destructive interference. This is what happens when you have a crest and a trough approaching each other. So positive 1 meter, negative 1 meter. When they meet, they add to 0. If you snap a picture of the spring at that instant, you would see it look like there aren't any waves there. There are waves. It's just that they're both at that moment overlapping up and down, and for that moment they add to 0. But the word destructive is a little misleading because they don't destroy in the sense of like, oh, if I destroy a glass, I smash it and it's broken and gone, right? This is not the case with waves. They momentarily add to 0, but then they emerge again, passing through each other. So they don't destroy each other in the sense that they're permanently gone. It's just at that instant. Related to destructive interference, noise-canceling headphones. Some of you may have these. What these do is they don't try and block the sound waves from getting into your ear. You can block sound waves with earmuffs or earplugs. So that definitely lessens the sound going into your ear, but noise-canceling headphones go a step further. So into your ear, let's suppose this dark wave represents the original noise. Maybe it's someone talking next to you, and you want to listen to the music that's playing on your phone, and so you want to not hear the person. So instead of blocking them, and by the way, this is drawn incorrectly. Sound waves don't have crests and troughs. They have compressions and rarefactions, but it gets really kind of hard to see if I draw accurately a sound wave that makes compression and rarefaction. So I drew it as a transverse wave sound, but it really isn't. Just a little side point, just to see what's going on with the noise-canceling headphones. So that's the original sound of the person next to you talking. You don't want to hear that. You want to hear the music. The headphones pick up that person's voice electronically. They analyze it and recreate that person's voice and broadcast it on top of the person's voice, the original voice. So it's replaying the person's voice to add to the original wave. You might say, well, that's going to make the person's voice now louder. It's going to amplify it. No, electronically what it does is it makes it 180 degrees out of phase. So while the person's voice is sending a compression into your ear, the headphones are sending the same sound but as a rarefaction into your ear. And those add to 0. When the sound from the person's voice is a rarefaction, the headphones are sending in a compression of that same exact voice. And so it's like a mirror image opposite, and it cancels the wave of that's the noise that you don't want to hear. It cancels it or makes a destructive interference, adds to 0. So what goes into your ear is silence. Okay, so that's the result, silence into the ear. Now, it's not perfect because when someone talks, any sound that or any sound that you hear, most of the sound goes in through your ear canal. But some of the sound also hits your body and travels through your body and goes into your ear. So the noise-canceling headphone can cancel what's going into your ear directly, but it cannot cancel sounds that go into your body and then into your ear. So that's why it's not perfect. All right, so that is the lesson for today. Principle of superposition. You add the amplitudes of two waves, some diagram examples where you might have to do that, right? You might have to do this on a test also. And then also this idea of constructive interference, when crest meets crest or trough meets trough to produce a bigger wave. Destructive interference when crest and trough meet to produce momentarily no wave. And then little application, noise canceling headphones. All right, see you in the next video.